All right, here's a summary for the solution to homework number 8 in ME370. All right, so problem 1, we have this bar. It's made of ANSI 4130 quenched and tempered at 600 degree Fahrenheit steel. And it's got a stress state of 60 KSI in tension in the X direction, 70 KSI in compression in the Y direction, and 85 KSI of shear. We want to find the factors of safety based on the maximum shear stress theory and the distortion energy theory. We want to plot a 3D circle as part of this answer. And then we also want to plot the failure loci and find by graphical estimate the factors of safety, both of them. And we want to compare the numeric and graphical safety factors. Okay, so starting out, it's a good idea to plot out the stresses that are on this thing. We might also want to, oops, I didn't have the book open. Interesting. Let me see. Let me go open up a copy of Shigley and look at the material properties. That's also a good thing. So I thought perhaps some students might have not be as familiar with the nomenclature of the material, but I want you familiar with that. So that's one of the reasons why I gave you sort of a different steel. I didn't go back to my standby A36 steel. So anyway, we could go into table. First off, we probably want to look at table A20. That's where the main material listing is right here. And I think my dog's about to bark. No, she's going to be okay. And you can see that, let's see, the material that we're asking for is 4130, that it's not in the table. So we want to keep looking, and we get into table A21 and come down, and there she is, 4130. And they said quenched and tempered, that's what the Q and T means. And they said at 600 degrees. And we want to get the yield strength, and we want it in US units. So it ends up being 200 KSI. All right, I'm sure I'm going to get some people answering with stuff from MatWeb. But anyway, so here it is, and I kind of think I copped out on this particular problem. I went ahead and I'm just posting up the Moore circle there. You can see that the center of it is just over to the side right here, but we've plotted out the points. Here's your 60 and your 85, and here's your 70 and your 85 over here on the compressive side. And here are some values. There's from the spreadsheet that I made of the thing. So you can see here's where the C was, R. It's a little tricky. I think I would go with this side to get the radius this time. And then here's your sigma A and your sigma B. So we had 102, like right there, and negative 112 is going to be what ends up being sigma 3. Right, and then so my tau abs max is going to be 1 minus 3, and then divided by 2. So I get 107 as KSI. And I don't know what that negative 5 is. I don't know what that number's just floating right there. But then, so here is the shear stress, or shear strength, shear yield strength. That's just 200 divided by 2. And so then we divide in our that by our 107, and we get 0.93, right? No more than 2 decimal places, please, for safety factors. And then here's my maximum. Here is my my von Mises stress, I should say, and I didn't bother writing that down, so maybe I should try to write that down. I don't know if I can write with my mouse, but the von Mises stress would be you would take okay, so this one is going to have to be, all right, so let me I should go back here 1 second. Sorry, I'll erase this part right there and keep writing. And so this equation we want to use this equation. Let me write out what the equation is first. Square root. Now you could actually do this in a couple different ways. I think the way that I would approach it, we could approach it because we already have principal stresses. I'll write it up above. We could do, so okay, I'll finish it eventually. All right, so here's the one with principal stresses. Whoops, yeah, we'll go right to here, and we'll go sigma A squared minus sigma A times sigma B squared. Now all of a sudden I'm going by memory, and I'm actually starting to doubt my memory here. I don't know, maybe I should start this recording over. Nah, keep it going. All right, so let's double check that we got this right one. Let me double check that my memory worked by looking up in Shigley. Always a good idea. See, I'll go Alt Tab. Will Alt Tab work? Yeah, Alt Tab. Yeah, bah. Used to use Alt Tab all the time to hide when you were playing like solitaire at work, right? Just have your hands on Alt Tab when the boss started walking by your cube. Yeah, it's not a very good role model, am I? All right, so yeah, so I didn't really say that, right? So here's in chapter 5 is failure prevention. And so maybe it's even a good idea to show what equations, where we're getting the equations out here. So there's a bunch of different equations for von Mises, but the main ones that we would want to use depending on the situation. If you had the principal stresses in 3D, this would be the one to go to, this guy right there. But if you already have the principal stresses in just 2 dimensions, the one I just wrote right there, and I got it right. Woohoo! So these are the A and B are the non-zero principal stresses. But now, if you don't already have the principal stresses, this is your go-to equation right there. If it's biaxial stress right there, so that's your von Mises. Now, they don't. Interestingly enough, they don't have what I would consider the most common scenario and the most common von Mises equation. And let's see, can I write it out with my comment tools? Well, let me do the comment tools. Let's see. If you have, let's see, where are you going here? Well, that's signing. I don't want to sign. I want to mark with my comment. Where did it go? There it is. Okay. Losing it. All right. So if you only have stress in a normal stress in one direction, you can get rid of that and get rid of that. And it gets your most basic von Mises equation, which looks like this right here. Right? And it's the most common. It's one that's probably worth memorizing. Because and this is only for the case of uniaxial stress, right? And you can see how that comes out. And it's interesting that Shigley doesn't actually write that anywhere, except maybe in one of the examples, I think. An example further down somewhere, I think they have, they actually use it. Maybe I'm wrong. Yeah, I'm probably wrong. But anyway, somewhere in one of these, I'm pretty sure they write. Yeah, okay, so they actually just show it getting used right there. They don't actually write out the equation. But anyway, this is an equation worth memorizing, this guy right here. And it's like the most simple, because it's the scenario that happens most often. So back onto this. So we're writing things out, aren't we? Yeah, okay. So the equation that we have to use in this instance, I think I'm going to get this right. Well, let me double check it. Sigma y squared plus 3, oops, I did that little thing, tau squared, right? And that's an x tau xy. Let me double check I got that right and give my Alt Tab again. And yes, I got it right. Okay, good. I got office hours coming up, which I meant to go to back to there. Okay, so all I've done right there is taken 60, and I got to make sure I get that negative in there, right? So we get that 60 squared plus, I don't know why I put that there. Okay, nope, not plus. Erase that. Why did I bother making a spreadsheet, a PowerPoint if I wasn't going to use, if I was just going to do this by hand? All right, 60 and then negative 70. That right there is like kind of key if you're going to use this equation versus this equation, right? But you can't use that one that I said was the most common one because we actually have biaxial stress. We actually have stress in two different directions. Now this negative doesn't matter right here because it's squared, but this one did, obviously, right? Ugh, I hate that damn thing. I looked up on the internet trying to figure out forever how to get rid of these stupid like little things that jump out. And I think I have it where you just have to write slowly, right? If you just write slowly in a smooth fashion, it doesn't do the little jerky thing, right? So go tap. Oh, I need to actually put a value in here. That's going to be the 85, right? So you put the 85 in here and square it. Boom. All right. So that's how I got this value right there, right? And then just divide the yield strength by the von Mises, and that gets us 1.08. And note that there's a 15% difference between those safety factors based on these two different theories. Well, it's a really good idea to plot this out on the failure loci here. And you can see why this happens, right? Because this stress point is in between the two, the maximum shear stress theory hexagon thing and the distortion energy oval, let's call it. And graphically, what I was asking for was you to like use a to plot it out by hand, and then just to get divide out the length getting to from here to there, right, and then to the point, and then also from here to here, and get those ratios of the distances you're physically measuring, and then compare it to what you got right here, right, with the safety factors. But I'd also was pointing out to you that that's lands in between there because we know it's right there in that gap. All right, so for problem 2, we have this pipe and it's loaded here at the end. Oh boy, they did a lot of those crazy little things this time. And it's made out of annealed stainless steel right there. So annealed 304 stainless steel. And we have the loads of 25 kilonewtons in the X direction and 40 kilonewtons in the Y direction and 10 kilonewtons in the Z direction. And it's got internal pressure of 12 megapascals. And the dimensions are 1.3 meters, 1.35 meters. B is 1 meter. C is, what is C? C is 2.3 meters. So it's a total of 3.3 right there. And then E is 1.6 meters. And I said to ignore stress concentration and ignore transverse shear stress. We want to find the safety factors against yielding at the section of interest right here. And plot out a 3D Moore circle as part of this answer to get the principal stress, to get the safety factors, right? And then we also want to plot out the failure loci using the non-zero principal stresses in here, and then do a graphical estimate and compare. Right, so it's a lot like this other problem, the first problem 1, except that we're actually going to calculate something out. So here's like sort of a general procedure. I've been trying to point out some, but we'll see it coming up here. Let's start out with the geometry first when you're approaching a problem. First, I got the thickness, right? Because they gave us the inside diameter and the outside diameter. So to find the thickness, just subtract the 2, divide by 2. And then we find out that it's 9 millimeters. And I'm going to want to know the radius of the outside. So I went ahead and found it. So to get the area, remember, you got to take the pi over 4 times outside diameter squared minus the inside diameter squared. And so here we get the area in meters squared. Here is the moment of inertia. Got to be careful. Make sure that you don't put that raise these powers to the outside right there. They belong on the individual ones, right? It'd be a different answer. So we get this, and then just because it's a symmetric, axial symmetric section right there, it's just 2 times I for the polar moment of inertia. And we might as well, by call it the part of the geometry, just assess whether it's thin-walled or thick-walled. 9 divided by 137.5, much smaller And I think I might be off, but I think that's an accident right there. I don't think it's 0.006. I think it's just 0.06. But it is less than 0.1, so whoopee, we could be thin-walled. We get the loads, right? So we did the geometry, now we do the loads. And do an FBD in the XY, it's a good place to start, right? So we're looking over from here with a creepy eye, right? Here's a creepy eye. Looking over from that direction. Some of the moments about the Z-axis, and we have the, sometimes I call this the reaction Z, so you think it's a different, the reaction moment Z instead, but you can see that we have, this is the one where we have actually, of the three free body diagrams for this problem, you'll see that one of them in the X direction is going clockwise, but it's competing with Y, which is going counterclockwise. So it depends on what the magnitudes were, but it does turn out that Z is in fact going to be counterclockwise, the reaction moment. Do it for the XZ axis. So now we're looking down at the thing, right, from up above. And some of the moments about the Y axis now to get the reaction, the reaction moment. And we could actually predict, because both the FX and the FZ will tend to be a counterclockwise moment. Therefore, I could recognize that my reaction moment needs to be clockwise. And I plug the values in there, and I get 53.5 kilonewton meters clockwise. And then lastly, I do the YZ axis. That's looking over from this direction right here at the thing. And we get to some of the moments about the x-axis, which turns out that's going to be the torque, by the way. And both of those are clockwise, so we know that the reaction is going to be counterclockwise. And we get the moment about the x-axis, which is torque. And here's like a summary of the applied loads, right? Here's the equivalent moments about the section of interest. What we've essentially done is moved these forces from where they're located here down to this section. And in the act of moving, we've shown that they have these moments. And all these moment directions are opposite from what we got from the FBD. Now, in this case, we're doing something differently than we've done in many other homework problems, and we're going to probably continue with this. We ignored transverse shear, and one of the reasons why we did is now we want to not just look at a particular element, we want to look at the worst case scenario, right? And the worst case scenario is going to be where there's the maximum bending moment, right? We're not looking at a specific spot. We have to find where that maximum is. And what that's going to be is we're going to combine MZ and MY into a total moment that the section is going to feel as a bending moment. And that's going to be rotating about a different axis, right? So it ends up being an axis similar to this. And what we will find is we're going to have tension right here and compression right there. So what we really care, though, about is the magnitude. So we can find the maximum by taking the square root of the sum of the squares and get that maximum moment. With that maximum moment and the torque and the force in the x direction, well, we can get axial. We know that's going to be tension. That's just going to be Fx divided by the area. We get the bending moment. The maximum is that maximum moment we got above, and these other parameters. And I'm doing this on the outside surface. I should mention that. I'm going to go back and just kind of mention just quickly that some students might have the insight or thought to check on the inside surface instead of the outside surface, which that's good. That's a good thing to instinct to check, and it kind of actually turns out to be an interesting thing. I didn't force you to do it. I don't mind if you didn't do it, but that is a very good insight that you should consider doing something on the inside surface instead of the outside surface. All right, so I'll explain why in a minute. But hoop. And once again, this is on the outside surface, so we don't use the one that's di plus t. And so we get this hoop stress, and then we get the longitudinal stress. Both of these are in thin-walled. And then torsional shear. And we use that torque that in a moment up here that we had before to get that. All right, so here's a summary of these stresses. Now we have to combine them, and it's going to be combined like right here at that location, right? Because that's going to be where there's going to be tension and from the bending. It's also going to be tension from the axial, which is relatively small compared to these other stuff, but it would be tension. And then we're also going to have longitudinal is in that direction. Longitudinal tries to make the thing longer, so therefore that's going to be an axial type stress, right? It's going to be in line with the axial stress, and that's along the x-axis. And then hoop, we know, is going to be perpendicular to that. It's going to be kind of like that direction right there. So I add those together to get the stress in the x direction, the total stress in the x direction. And I show that down here. And you also note that I didn't put a vertical coordinate. I just put a coordinate in the x direction, because this actually isn't the vertical part of this little element that we see isn't really aligned with either the y or the z. It's somewhere in between. But here is, getting a stress element and getting all of the three main stresses onto it is summarized right there. So now I want to do the principal stresses. And here is the Mohr circle. Here's where I've plotted out this face right here. And then I've plotted out this face right here. This face. Right there, and got the three main Mohr circles, but this is one of the main guys that we want to care about. So I found the center was going to be right here, so that's like 192.7. I got the radius. I think I decided to use which one? I guess I used the center, right? The center minus this guy. So it was actually this guy that I used for the radius. So here was the center on there. And then I got the principal stress A, that one right there, from taking the center plus the radius. And then for B, it's going to be this one right here. I got the center minus the radius. And then obviously the third principal stress is 0 here. And so the tau abs max is just the first principal stress minus the third principal stress, which is 0, divided by 2, right? So it's 147.6. Now for von Mises stress, I'm using this equation right here. I could just as easily, because I have the principal stresses, use the other one, the other equation that I mentioned previously. So here you go, 261.9. And the safety factors now that we would get, I want to get the material properties. Sometimes I do this in the very beginning, but we need to use the annealed, use a different table. So I use table A22 this time. Let's look in Shigley here. Where'd you go, Shigley? Okay. So we'll go to the material properties over here in the appendix, and there's, steel's mostly, I guess entirely, in that A20 and A21. But if you go to A22 here, you'll see that we have for some metals, and you'll have 304 stainless steel annealed. So its yield strength is going to be 276. 276. All right. And so that's where that came from. And so for the maximum shear stress theory, you take the shear yield, which is the normal yield divided by 2, and then you divide it by the absolute maximum shear. And then let's see, I gotta look at my time. Well, I need to get on to collaborate. So here's my safety factor, but we only want to use 2 decimal places. So there you go. And here's the distortion energy theory. It's just the yield strength divided by the von Mises stress. So here is the answer. And here's what it looks like plotted on a failure loci. And once again, I purposely made it fall short in between there. So it should be pretty close. You'll notice, though, that the distortion energy theory and the maximum shear stress theory are 12.7 apart from each other. All right, so we will discard all of that. But one thing I did want to mention. Okay, so I calculated this in Excel, as I often will do. So, and then I did like outside versus inside. So here's all my values for outside. And then I recalculated for inside. So the things that are going to change is, instead of for this one, I used the outside diameter for the C. This one I used the inside diameter, right? And then another one that's different is going to be for hoop. Instead of using the average, which is DI right in there, I use the DI plus T. All right, so the hoop on the inside surface is larger, but it's only about 6 megapascals larger. The torque is going to be less because it too uses the inside diameter for the radius that's in the TR over J in the R part. And then the last thing that's going to be different is now the principal stress is going to be the third principal stress is going to be -12, right? And so for von Mises, it actually, it reduces the, so von Mises stress. Now the equation to use is this one right here, because we have all 3 principal stresses. We need to use this equation now instead of the other forms of the equation. And then let's see, did I say that wrong? I think I must have said that wrong. Okay, here I said, okay, the absolute maximum shear. I'm sorry, I do that out and I actually get something, I get a higher stress. So I get a lower safety factor there. But interestingly enough, when I apply this von Mises, I actually get a safety factor that's a little bit higher than the distortion energy theory. So I decided it wasn't important to do this, right? So I selected not to include it. So, but either way that you do is fine with me. I'm totally okay with, but I really like that you would check it, because we didn't know. We just asked for the maximum, and we didn't know I don't know if I said it was on the outside surface. Maybe I did say it was on the outside surface. Let me double check. Let me see what the problem said. I got to get logged on to collaborate right here. Find against at a section of interest. It didn't say on the outside surface, so that would have been very insightful for you to have checked the inside surface instead. So thank you.